Picture yourself in a medieval workshop, building a grand siege engine that will lob heavy stones over a castle wall. Someone asks you, so what launch angle should we use for maximum range? It's a question that immediately brings to mind the familiar result from introductory physics. A 45-degree angle yields the longest distance for a projectile launched at a given speed, at least in a vacuum with no air resistance. But in the real world of wood rope and counterweights, it's not quite that simple. Let's start with the classic theoretical principle. If you ignore air resistance, the maximum range on flat ground is reached at 45 degrees because that angle maximizes the product of vertical and horizontal velocity components. Concretely, if you launch a projectile at, say, 20 meters per second at 45 degrees, you can use the standard formula for projectile motion to show it travels farther than if you use 30 degrees or 60 degrees. You might ask, why is that so optimal? The answer is in the factor at 45 degrees is 1, giving you the biggest possible multiplier of your initial velocity squared. Of course, there's a catch. Real catapults aren't just simple launch tubes. They're powered by a dropping counterweight, and the amount of kinetic energy transferred to the projectile depends on two main factors: the weight of the counterweight and the height from which it falls. Suppose you're flinging a stone that weighs 10 kilograms and want it to leave the throwing arm at a speed of 20 meters per second, about 72 km/h. To achieve this, the stone needs to gain around 2,000 joules of kinetic energy, which depends on both its weight and how fast it's moving. However, medieval catapults made of wood and rope weren't very efficient at transferring energy. If we assume an efficiency of around 50%, meaning only half of the energy from the counterweight drop is actually transferred to the stone, then to provide the stone with 2,000 joules of kinetic energy, the counterweight itself needs to release about 4,000 joules of energy when it falls. This energy comes from the weight of the counterweight and the height it drops. So, for example, a 200-kilogram counterweight dropping from 2 meters would provide enough energy, just as a 400-kilogram counterweight dropping from 1 meter would achieve the same effect. In other words, a heavier counterweight can fall a shorter distance to achieve the same result, while a lighter counterweight needs to fall from a greater height to generate enough energy for the launch. In other words, a heavier counterweight can fall a shorter distance to achieve the same effect, while a lighter counterweight needs to fall from a greater height to generate enough energy for the launch. Now you might ask, if 45 degrees is best for raw distance, does that mean every medieval engineer set their catapult to 45? Not exactly. Siege conditions are rarely about raw horizontal range alone. You might need to arc a shot over a 10-meter high wall. Or maybe you want a flatter trajectory that strikes a wooden door with maximum horizontal speed. Higher angles, like 50 or 55 degrees, sacrifice some total distance, but let you lob the projectile with a steeper curve, potentially clearing battlements more effectively. A lower angle around 30 degrees flies a shorter path, but can slam targets more directly. So the textbook optimum of 45 degrees is just one factor among many in actual siege strategy. Then there's the matter of your counterweight design. If you keep increasing that mass, let's say jumping from 200 kilo to 400 kilo, you could, in principle, impart more velocity to the stone. Wouldn't that just keep increasing my range, you might wonder? To some extent, yes, but your catapult's arm can only handle so much force without breaking. You also need enough structural heft to survive repeated firings. So in a real engineering scenario, the question becomes, how heavy can I go while still keeping the machine reliable? And that might lead you to tweak your launch angle away from a perfect 45 degrees to accommodate the slightly unpredictable speeds that result from heavier or lighter drops. Finally, air resistance can't be fully ignored in large stone throws. You might see angles slightly under 45 degrees chosen to compensate for drag, since a real chunk of rock isn't aerodynamic. Also, the ground isn't always perfectly level, so a catapult on a slight uphill or downhill shifts the effective best angle. Throw in the practicalities of maintaining tension in ropes or distribution of forces on the arm pivot, and your nice, clean formula starts to look like just one piece of a bigger puzzle. So if someone demands a quick theoretical answer, which angle precisely, you can wave that 45-degree flag. But if you're the medieval engineer, you'll probably ask additional questions. How high is the wall? How big is my counterweight? How strong is my catapult's frame? Is my projectile aerodynamic or just a rough stone? Then you'd adjust from that 45-degree baseline. The interplay between counterweight mass, arm length, pivot placement, and the projectile's shape all factor in. After some trial shots monitoring how far the stone actually flies, you'd fine-tune the release angle until you find a sweet spot for that particular machine. In short, yes, the classic rule of projectile motion says 45 degrees maximizes range for a given launch speed. But your actual catapult is an evolving puzzle of angles, counterweight sizes, mechanical stress limits, and siege requirements. That's where medieval and modern engineering prowess meets the neat formulas of physics. Sometimes you deviate from the textbook optimum to suit the battlefield or your stone-slinging goals. And that's exactly what gives catapult design its timeless challenge and appeal.
Subscribe it.